So this first example here is nothing new really. All that we're introducing is that we've got some boundary conditions here where we can work out our constants A and B. Okay, so solving this exactly the same way as we did last lesson. First thing to do is to find the complementary function. And to find the complementary function, we start off with the auxiliary equation from the left-hand side. So I've got lambda squared plus 2 lambda plus q equals 0. So using the coefficients from the left-hand side, the coefficients are quadratic, and we're going to solve this. You can solve it in the calculator, that's fine. That's -1 plus or minus. We've got complex roots, so this tells us that our complementary function has the form y equals e to the real part of x minus e to the minus x minus 1x, and then times by a cos of the imaginary part x, which is just 1 in this case, so a cos x plus b sin x. Okay, make sure you learn those forms. Next bit is to think about the particular integral. So looking at the right-hand side then, we're going to try y equals something to do with trig functions, and it has to include both sine and cos because we've got sine on our right-hand side. So y equals p sine x plus q cos x. Differentiate this twice and then substitute it in. So dy by dx gives you p cos x. Minus q sine x, so we differentiate cos, and differentiate it again, gives me minus p sine x minus q cos x. Substitute those into the differential equations, so we've got d squared by dx squared, so it's minus p sine x minus q cos x. And then plus 2 dy by dx, so plus 2p cos x minus 2q sine x. Do you guys find it somewhere else? And then plus 2y, so plus 2p sine x plus 2q cos x, and this is equal to 5 sine x. We're going to collect up all of our sines and coses now. So let's do find first. So sine x, we have minus p from this one. We've got minus 2q from that one, and we've got plus 2 from there. Coses, we've got minus q plus 2p, those two, and last one plus 2q equals 5 sine x. We can equate these coefficients and then get simultaneous equations for p and q. So the sine x is equal to 5, so we've got minus p plus 2p, which gives me p minus 2q equals 5. From the cos, collecting up the q's gives me 2p plus q equals 0, and then you can solve these in your calculator. So you get q is minus 2 and p is 1. This tells you that your particular integral is y equals sine x minus 2 cos x. Put all this together for your general solution. The general solution is our complementary function, which was e to the minus x, a cos x plus b sine x, plus our particular integral, which is sine x minus 2 cos x. This is all we did, yes. Now we have boundary conditions though to work out A and B. So first off in this question, it tells us that y is 1 when x is 0. Let's use that first. So substituting those in. So y is 1, x is 0, cos 0 plus b sine 0 plus sine 0 minus 2 cos 0. A lot of it does end up being 0, so the sine zeros end up being 0. Cos 0 though is 1, so we get 1 equals e to the 0 is 1 as well. So this is just a, and then minus 2, which gives us a. Then in the question, it also tells us that dy by dx equals 2 when x is 0. We're going to use that as well. To get dy by dx, I'm going to differentiate my general solution and then substitute it in here. You can use your a value one now that you've worked it out. It's just a bit of a pain. So dy by dx equals, I've got to use the product rule to differentiate this one. So e to the minus x goes to minus e to the minus x. A is 3 cos x plus b sine x. Then differentiate this bracket times by e to the minus x. So e to the minus x minus 3 sine x plus b cos x. Differentiating the sine x goes to cos x. Differentiating the cos x goes to minus sine x. So you get cos x plus 2 sine x. That's me differentiating my general solution to get dy by dx. Now I'm not going to simplify this. I mean, you could factorize e to the minus x if you really want to, but I'm not going to. Now I'm going to substitute in dy by dx equals 2 and x equals 0. Zero in the right hand side, so plus e to the 0 minus 3 sine 0 plus b cos 0 plus cos 0 plus 2 sine 0. All the sine zeros end up being 0. There we go. E to the 0 is 1. Cos of 0 is also 1. So we have 2 on the left hand side. Minus 1 times 3 times 1 gives me minus 3 from that first bracket. 1 times 1 gives me plus 1 from the second bracket. Sorry, not 1, it's plus b from the second bracket. And then I've got plus another 1 from that cos 0. But so let's add the 3 across minus the 1, you get b. Finally, after all of that, you write down your particular solution, which is y equals e to the minus x. A we found to be 3, so 3 cos x. B we found to be 4, so it's 4 sine x plus sine x minus 2 cos x from our particular integral earlier on, that's right. These questions are long. There's a lot of opportunities for you to make mistakes and slip ups and things like that. You've just got to be super accurate. I don't think there's anything massively difficult in it. It's just how much writing you have to do. That's the annoying. How many marks? A lot. Around 10-ish. Now we're going to look at what happens when we get down to the particular integral step. And there's something that wasn't on that table from the previous lesson, or there's a problem with it. Okay, so this first one is for a non-standard particular integral. Non-standard just means it wasn't on the little table that I gave you last night. So for this differential equation, the right-hand side isn't one that was on the table. It's a linear function times an exponential. Basically, that's what we're going to try for our particular integral. Okay, and this one, I would expect if you get a question with a non-standard particular integral, they will give you what it is. So it tells you what the form for the particular integral is. It wants us to work out values of p and q. So exactly the same way as we normally would for particular integral, we're just going to differentiate this expression twice and substitute it in. So y equals px plus q e to the minus x. I'm going to differentiate this one using the product rule again. So differentiate the inside of this gives me p by e to the minus x. And then plus differentiated e to the minus x and p q. I am going to factorize this because I think it will make my life slightly easier further down the line. So I'm going to take out the e to the minus x and put p minus px minus q. Differentiating this second time, again using the product rule, so differentiating e to the minus x goes to minus e to the minus x times by p minus px minus q. And then plus differentiate the second bracket times by the first. So differentiating that gives you minus p e to the minus x. And again, I'm going to combine this together. So I'm going to factorize out the e to the minus x to give me, so that'd be minus p plus px plus q minus another p, because that minus is on all of that. So I'll write this as e to the minus x px plus q minus 2p. Let's take these and substitute them back into the original differential equations. So we had d squared over dx squared. What is this? E to the minus x. X plus q minus 2p. Plus 5 dy by dx. So minus 5 dy by dx. Which is e to the minus x, p minus px minus q. And then plus 6y. Px plus q e to the minus x equals the right hand side, which is 12x minus 7 e to the minus x. Everything has e to the minus x on, so let's get rid of that. And then I'm going to collect up my x's and my number terms. So in terms of x's, I've got px from this first bracket, that one. I've got minus 5 times minus px. That's plus 5p from here. And I've got 6 times p from my last bracket. Yeah. So that gives me 12px. My other terms, my number terms, so I've got plus q minus 2p here, minus 5 times p, so minus 5p, and minus 5 times minus q gives me plus 5q from this one and this one, and I've got plus 6q from this one. And this is equal to 12x minus 7. Let's collect up all of these terms in red. So I've got q plus 5q, which gives plus 6q, which gives me 12q. And I've got minus 2p minus 5p, which gives me minus 7p. It's 12x minus 7. Equating the coefficients on these. So that tells you that 12p is equal to 12, so p equals 1. And if you stick that in there, so you get 12q minus 7 times 1 equals minus 7. 7's cancel, so that gives you q equals 0. So the particular integral is y equals p is 1, q is 0. So it was px plus q times e to the minus x. So you just get x e to the minus x. An awful lot of words, just get 1 and 0. It then wants us to find the particular solution satisfying the boundary conditions x equals 0, y 0, dy over x equals 0. So I'm going to go back and do the complementary function for the first bit. Does anybody object to me rubbing this on? Thank you. So we found that the particular interval was y equals x equals. Right, finding our complementary function, we're going to start off with the auxiliary equation from the left-hand side. So lambda squared minus 5 lambda plus 6 equals 0. Which gives you two solutions. Lambda is 2 or 3. But two real and distinct solutions. So that gives you a auxiliary equation, sorry, complementary function of the form y equals a e to the 2x plus b e to the 3x. Put this together for our general solution. So general solution is just these two things added up. So a e to the 2x plus b e to the 3x plus x e to the minus x. Then using our boundary conditions. So boundary conditions say when x is 0, y is 0. Sum all that in, that a is e to the 2 times 0, b is e to the 3 times 0. 0 times e to the minus 0. Obviously, this last bit ends up being 0. E to the 0 is 1, so you get a plus b equals 0. As far as I can get for now. Then we also know that dy by dx equals 0 when x equals 0. So differentiating this to get dy by dx is easier than last time we did this. 2a e to the 2x plus 3b e to the 3x. Product rule on x e to the minus x. So differentiating x gives you 1 times by e to the minus x. And then differentiating e to the minus x goes to minus e to the minus x. Let's sub in our zeros. The divide x is 0. X is 0. E to the minus 0. Minus 0, e to the minus 0. So that last term ends up being 0 because it's times by 0. But all the e's are just 1. So 0 equals 2a plus 3b plus. Got a pair of simultaneous equations to solve here. You can solve them in your calculator. That's fine. I can solve them by hand. You end up with b is minus 1 and a is. So our particular solution, sub these values in. So y equals, we've got a is 1. So e to the 2x minus b, because b is minus 1, so minus e to the 3x plus x e to minus x. That's the last one was solving. Like I said, if you have a non-standard particular integral, they will give you it in the exam. There are situations where what you would usually choose to be a particular integral will not work, will fail. So we're going to look at an example of this. So we've been asked to find the general solution to this equation here. So let's just start off really quickly with the complementary function. And our auxiliary equation is 2 lambda squared minus 8 lambda 0, which if you solve this, you get 3 and 1. This gives you your complementary function is of the form y equals a e to the 3x plus e to the x. You'd then go and do particular integral, as you normally would. So for particular integral, we are going to try y equals p e to the x, because this right-hand side is just of the form e to the x. So we try something times e to the x. Differentiating this twice is easy, stays the same, e to the x, and second derivative is also x. So if we substitute these in, that gives us 2p e to the x minus 8p e to the x plus 6p e to the x equals e to the x. We can cancel e to the x off all of this. Leaves 1 on the right hand side. But the left hand side 0. That's a problem. 0 is not equal to 1. The issue that we have, it says underneath, but the issue that we have is that the particular integral, p e to the x, we already have that in our complementary function with a different constant. We've already got just something times e to the x, just a constant times e to the x. Okay, so this is a problem, and you can see it doesn't work. It means we need to. It just means we need to try a different particular integral. Okay, so notice we always say try for a particular integral because there are other things that could work. So now, basically, your strategy is you try the same thing but times by x. That's generally what the strategy is. Okay, so now we're going to try instead a new particular integral. Y equals px e to the x. Bit more annoying because we've got to use the chain product rule to differentiate this. So differentiating px equals to p times by e to the x. Differentiating e to the x stays as e to the x. So it gives you that p dy by dx. D squared r by dx squared. Differentiating p e to the x stays the same. Differentiating px e to the x we've just done, so I'm just going to write that down the same thing. And you can simplify this to be p e to the x plus 2. So 2p e to the x plus px. Right, let's try substituting this in now. So we've got 2 lots of d squared over dx squared, so that gives me 4p e to the x plus 2px e to the x. We have minus 8 dy by dx's, so minus 8p dx minus 8px e to the x. And we have 6 y's plus 6px e to the x equals e to the x. Get rid of all the e to the x's and start collecting up our like terms. So collecting up our x terms, we have 2p from here, we have minus 8p from here, and we have plus 6p from here. And so that just disappears, which is correct what we were hoping for because there's no x on the right hand side. Then our number terms, we have 4p, this one, we got minus 8p from this one. And that's it in terms. So the x terms disappear. This bracket, there's 2p minus 8p plus 6p is equal to 0. But here we've got minus 4p is equal to 1. And it has worked out. We worked out p is minus a quarter. And so you can see it's going to work for me. I'm not going to finish off the full solution, but it is going to work. In general, this doesn't come up very often. But in the case where your normal particular integral would also be included exactly in your complementary function, you need to try something else, basically times by x. So there are 5 here. We're not going to solve these 5 differential equations. What we're going to do is work out what our complementary function is and what our trial integrals are, and stop there. We're not going to solve them fully. So this first one, complementary function, start off doing the auxiliary equation, which is lambda squared minus 6 lambda plus 9 equals 0. This will give you a repeated root at 3. So your complementary function is of the form e to the 3x times ax plus 3. This is a problem for our particular integral. Usually you would try y equals p e to the 3x, but you can't here because you've got this b times e to the 3x. It's already included in your complementary function. So usually what you would do is times your normal particular integral by x. So usually you try px e to the 3x, but this is also an issue in this one because we've already got ax e to the 3x. So we times it by x again. So we're going to get px squared e to the 3x. Now this is fine. We can substitute that in. A lot of the terms will end up kind of cancelling out. But basically you just keep times by x until it works. Number 2, down here, so complementary function, we've got lambda squared plus 9 equals 0. So this gives us lambda plus or minus 3. I complex roots for this one. So our complementary function is of the form e to the real part, which is 0 in this case. So it's e to the 0. So there's actually none of that. And then a cos 3x plus b sine 3x. Now, usually for this form, 3 cos 3x, your particular integral would be y equals p cos 3x plus q sine 3x. But we can't do that in this case because that is basically the same as our complementary function. So I'm going to times it by x. So we've got px cos 3x plus qx sine 3x, and then you try that. The third one over here, complementary function. So we've got lambda squared minus 2 lambda minus 8 equals 0. Gives you 2 solutions. Lambda is 4 minus 2. Give you complementary function of the form a e to the 4x plus b e to the minus 2x. Our normal particular integral for this would have been p e to the 4x, but we can't do that because of the a e to the 4x. So our trial particular integral is going to be p x e to the 4x. This is fine because there's no x terms in your complementary. On to 4, complementary function. So auxiliary equation is the same one as before. So we still get lambda is 4 minus 2. Still get y equals a e to the 4x plus b e to the minus 2x. Difference is the right hand side no longer has the same power as the left, as the complementary function. So right hand side is e to the 3x. There's no problem with us choosing y equals p e to the 3x for our particular integral this time because the powers are not the same. Last one of these, so complementary function, we've got auxiliary equation of lambda squared minus 4 lambda plus 13 equals 0. You can solve this in your calculator. So minus 3i. So y equals e to the 2x a cos 3x plus b sine x for complex roots. Although we've got e to the 2x here in both of them, there's no problem with us choosing y equals p e to the 2x because these aren't just e to the 2x terms, they've also got that cos x not sin x term. So this one's just normal, you can just choose p e to the 2x. That's this differential equations part 1 pack finished.